What truly lies beyond the visible horizon of our solar system? Our immediate stellar neighbors offer us a glimpse into the cosmic expanse, but their proximity simultaneously challenges our comprehension of distance and scale. The Alpha Centauri system, our closest interstellar neighbor, is a fascinating triple-star system holding captivating possibilities, perhaps most notably Proxima Centauri. As the nearest star to Earth, this small, cool red dwarf harbors a validated exoplanet, Proxima Centauri b, orbiting within its habitable zone. Can it support life, or do its intense stellar flares render it barren? To put this journey into perspective, reaching the Moon takes days, and traveling to Mars requires months. Yet, interstellar scale is entirely different. Alpha Centauri lies a staggering 4.37 light-years away, a distance so immense that even at the velocity of our fastest spacecraft, the journey would take over 70,000 years. What secrets are hidden in those incredible gulfs of time and space, and how do we even begin to cross them? It's a long story, but we'll start it in a dream. Before we dive in, don't forget to like and share. While there are countless stars nearby, only a select few qualify as our true neighbors, and the Alpha Centauri system holds the title of the closest. This triple-star system is composed of Alpha Centauri A, Alpha Centauri b, and Proxima Centauri, each with unique characteristics. Proxima Centauri is the nearest star to Earth, at about 4.24 light-years away. It is a red dwarf, smaller and cooler than our Sun, yet capable of nurturing planets. For example, Proxima Centauri b is a validated exoplanet located in the star's habitable zone, defined as the orbital region where liquid water could potentially exist. Proxima b is slightly larger than Earth and has an orbital period of about 11.2 Earth days. However, its close proximity to the red dwarf poses a challenge. Intense flares and radiation may strip away its atmosphere over time, diminishing its habitability potential. When we talk about distance, we often think in miles, kilometers, or even astronomical units, but the interstellar scale vastly exceeds our everyday experience. The nearest stars are so distant that measuring them in kilometers becomes virtually meaningless. Instead, astronomers rely on the light year, the distance light travels in 1 year, approximately 9.46 trillion kilometers. For context, the Moon, our closest celestial body, is only 384,000 kilometers away, reachable by spacecraft in just over 3 days. Mars, depending on its orbit, ranges from a closest approach of about 54.6 million kilometers to a farthest of 401 million kilometers, requiring months to reach. Even so, this is a mere hop compared to traveling to the nearest star system, Alpha Centauri, which is about 4.37 light-years distant. At current flight speeds, reaching Alpha Centauri would take upwards of 70,000 years. This astonishing timescale illustrates that the barriers to human interstellar travel are not merely distance, but a complex challenge involving time, energy, and technological innovation. The system's 2 other stars, Alpha Centauri A and B, form a tight binary pair orbiting a common center of mass, creating a dynamic gravitational environment. They have no confirmed planets yet but remain prime targets for future reconnaissance due to their proximity. Beyond Alpha Centauri, several other nearby stars command attention. Barnard's star, renowned for its high proper motion relative to the Solar System, may host a candidate planet, Barnard star B, orbiting outside the habitable zone. Further out, Wolf 359 is faint and difficult to observe but provides an excellent opportunity to study the dynamics of smaller, cooler stars. Finally, Lalande 21185 is an exciting target due to its potentially habitable planet, Lalande 21185b, expanding the human imagination of nearby systems. Before we can launch our voyage, we must first understand the stars. Observing and studying stars requires overcoming the limitations of distance, brightness, and the atmospheric turbulence of Earth. Astronomers rely on a variety of techniques and instruments to unlock the secrets of our stellar neighbors. The first hurdle is measuring distance, which is primarily done using the parallax method. As Earth orbits the Sun, nearby stars show a minute shift in position relative to more distant background stars, forming the basis for distance measurement. By measuring this extremely subtle shift and applying geometry, astronomers can determine stellar distances with high accuracy. Parallax remains the most reliable method for distances up to several hundred light-years. Stellar spectra hold a wealth of information. Spectroscopy breaks down starlight into different wavelengths, revealing the star's temperature, chemical composition, and motion. For instance, the gravitational wobble of a star caused by an orbiting planet leads to periodic shifts in its spectral lines. This method has been crucial in identifying exoplanets like Proxima Centauri b and Lalande 21185b. While ground-based telescopes are limited by atmospheric turbulence, space telescopes like Hubble, Kepler, and James Webb circumvent these obstacles, offering unparalleled views of nearby stars and their planets. The James Webb Space Telescope, in particular, has the power to analyze the atmospheres of exoplanets for potential biosignatures, advancing the search for habitable worlds. Directly imaging exoplanets is a major astronomical challenge, but future instruments promise to capture detailed images of planets around nearby stars, revealing their surface environments and atmospheric composition. Humanity's curiosity about the stars dates back millennia. Ancient Babylonians, Egyptians, and Greeks viewed stars as unchanging points of light, imbued with mythological and spiritual significance. Early thinkers like Aristarchus of Samos and Hipparchus made early measurements that laid the groundwork for future understanding. It was only during the Renaissance and with the invention of the telescope that we began to truly grasp the nature of stars. When Galileo looked up in 1609, he shattered the ancient belief in immutable stars, discovering that the Milky Way was a dense river of countless stars and that the universe was far vaster and more complex than imagined. In the 19th century, William Herschel mapped the distribution of stars and proposed that the Sun was part of a larger galactic structure, reshaping our cosmic view. The mid-19th century saw Kirchhoff and Bunsen pioneer spectroscopy, allowing for the first chemical analysis of stars. The 20th century brought the realization that targets like Alpha Centauri were not just distant points, but other suns, possibly with planetary systems. The discovery of the first exoplanets in the 1990s opened the floodgates for imagining habitable worlds around these stars, and these breakthroughs inspire our modern quest to understand and reach our nearest stars. Astronomy is not solely the domain of professional scientists. Citizen science allows the public to participate in major discoveries. Platforms like Zooniverse encourage amateurs to examine telescope data for potential exoplanets, variable stars, are transient events. A famous example is the unusual dimming of Tabby's star, discovered by participants in the Planet Hunters project. While not in our immediate stellar neighborhood, this highlights the unexpected insights that collaboration can yield, while also raising public awareness of the challenges in deep sky research. Understanding the nature of our nearest stars requires a grasp of the stellar life cycle. These nearby neighbors span different stages of stellar evolution, offering invaluable clues to how stars are born, live, and die. Red dwarf stars dominate the universe, making up about 70% of all stars. They are small and cool, burning their fuel incredibly slowly, and can live for hundreds of billions of years, far longer than the Sun. Despite their stability, the intense flares of red dwarfs can challenge life by stripping the atmosphere of planets in their habitable zone. Solar-type stars display a more familiar stage of evolution with stable luminosity, providing excellent samples for studying the formation and evolution of Sun-like planetary systems. Dying stars offer a glimpse into the Sun's ultimate fate. The nearby star system Sirius, the brightest star in our night sky, hosts a white dwarf companion, Sirius B, a dense stellar remnant, the collapsed core of a massive star, which acts as a natural laboratory for studying stellar death. The void between the stars is not empty. The interstellar medium fills the space between stars with tenuous gas, dust, and radiation. Although sparse, it dictates the life cycle of stars and planets, acting both as the nursery for new stars and a hurdle for interstellar exploration. In dense regions, gravity causes gas and dust to collapse, igniting nuclear fusion and lighting up a star. Observing nearby stellar nurseries, such as the Taurus molecular cloud, reveals how stars like Proxima Centauri were born billions of years ago. However, the interstellar medium is not a tranquil vacuum, it is filled with cosmic rays, magnetic fields, and high-energy particles. For a spacecraft journeying to Alpha Centauri, even the low density of particles and dust can erode or damage a high-velocity vessel over time, necessitating advanced shielding and engineering innovation. Conversely, the medium also holds clues to the building blocks of life, with detected organic molecules suggesting that the precursors to life may be widespread throughout the cosmos. Researching these molecules aids our understanding of the chemical conditions that could nurture life around other stars. Technological advances are continuously pushing the boundaries of what is possible in studying and reaching our nearest stellar neighbors. Breakthrough concepts, such as Project Starshot, propose using powerful lasers to propel wafer-sized spacecraft to 20% of the speed of light, potentially, allowing them to reach Proxima Centauri in just over 2 decades. A different, crucial path involves interferometry, which combines the light collected by multiple telescopes to simulate a single, massive aperture. Missions like the European Space Agency's Gaia, with its precise mapping of stellar positions and motion, are laying the vital groundwork for these grander schemes. Parallax and spectroscopy are our fundamental tools for unlocking the mysteries of the cosmos, especially concerning our nearest stellar neighbors. They allow us to measure distance, composition, and even celestial motion, forming the essential foundation for interstellar exploration. Parallax is a simple yet supremely precise method of distance measurement. As Earth orbits the Sun, a nearby star appears to shift slightly against the distant background. By relying on geometry and the scale of the Earth's orbit as a baseline, its distance can be calculated. Even for the closest stars, this angle is minuscule, measured in milliarc seconds, requiring high-precision instruments to capture, as is the case for Proxima Centauri. One idea for improving future parallax accuracy is to extend the baseline beyond Earth, conducting parallax measurements from the Moon or Mars, where the larger orbital separation would yield even greater precision and provide a deeper map of our immediate galactic neighborhood. Of course, as distance increases, the parallax angle becomes too small for current technology to measure. Astronomers then pivot to standard candles, such as Cepheid variable stars, to gauge the distance to more remote stars and galaxies. However, for nearby systems, parallax remains the indispensable gold standard. For exoplanet systems, parallax provides crucial information about the scale and distance of the star and planet, which, when combined with transit photometry and other methods, allows for a more comprehensive assessment of habitability. Combining parallax with proper motion data allows us to reconstruct the star's trajectory relative to the Sun, revealing the galactic dynamic history, including close stellar encounters that may have affected our solar system. Spectroscopy perfectly complements parallax, focusing on the light an object emits or absorbs. It breaks starlight down into its constituent wavelengths, yielding the chemical composition, temperature, and motion of stars and planets. Observational range spans the visible, ultraviolet, and infrared, with the infrared being particularly effective for studying cooler objects and regions obscured by interstellar dust. The core value of spectroscopy lies in its chemical fingerprint. Every element emits or absorbs light at specific wavelengths, leaving a unique spectral signature. Analyzing these lines tells astronomers what stars and planets are made of. For exoplanets, when starlight passes through a planetary atmosphere during a transit, the spectrum can reveal gases like oxygen, methane, or water vapor, potential indicators of habitability, or even life itself. The Doppler effect enables spectroscopy to measure velocity. As a star moves toward or away from us along our line of sight, its spectrum experiences a blue shift or red shift, respectively. The slight gravitational tug of a planet causes a star's periodic wobble, leaving a recognizable rhythm in its spectral lines, which has been key to discovering many exoplanets. On a grander scale, measuring the redshift of galaxies allows astronomers to determine the recession velocity caused by the universe's expansion, offering insights into cosmic history. Even on the level of nearby stars, spectroscopy provides essential data, such as helping to disentangle the light from multiple stars in a binary system and determine their orbital characteristics. In pulsating variable systems, parallax and spectroscopy work in tandem. Parallax gives the distance, and spectroscopy reveals the relationship between the pulsation period and intrinsic brightness, collectively strengthening the cosmic distance ladder. Technological innovation has significantly boosted the precision of both techniques. Laser interferometry and adaptive optics have improved ground-based parallax measurements, while space platforms eliminate atmospheric distortion to enhance spectral quality. Although ground-based observations are constrained, advanced phase correction and data processing still yield a vast amount of valuable data. Traveling through interstellar space also presents challenges. Dust and gas scatter and absorb starlight, complicating parallax and spectral measurements. Yet, this interference simultaneously offers an opportunity to study the composition and density of the interstellar medium. Looking back, the first successful measurement of stellar parallax by Bessel in 1838 for 61 Cygni marked a major astronomical milestone. Early spectroscopic studies of the Sun and stars laid the foundation for understanding the chemical and physical nature of the universe. Spectroscopy can even reveal stellar surface phenomena. Changes in spectral lines over time can signify sunspots, informing us about a star's rotation period, activity cycle, and magnetic dynamics. The Gaia mission has pushed parallax to a new level, precisely charting over 1 billion stars and creating a three-dimensional map of the Milky Way, which is set to revolutionize our understanding of its structure and motion. Concurrently, spectroscopy drives our ability to identify the chemical building blocks in star-forming regions and the material origins of nascent stars and planets. The speed of light is often called the ultimate cosmic speed limit, a core tenet of Einstein's theory of relativity. Any object with mass cannot reach or exceed this speed. The faster an object moves, the more energy is required, and this demand rises exponentially as the object approaches the speed of light. Reaching 90% of light speed demands staggering amounts of energy. 99% is virtually impossible with current technology, and accelerating a spacecraft to even a fraction of light speed would require energy far exceeding humanity's current annual output. This leads to time dilation. As speed nears the velocity of light, time slows down for the spacecraft relative to Earth. For the crew, a journey lasting months or years could mean that far more time has passed back on Earth. While seemingly beneficial for the traveler, this temporal misalignment between ground and vessel complicates communication and coordination, critical elements for interstellar missions. The speed of light also anchors causality, the established order of cause and effect. If superluminal travel were possible, it could theoretically lead to paradoxes where the effect precedes the cause, which is not merely a philosophical issue but would force us to completely rewrite the laws of physics. Scientists universally agree that the universe must uphold causality to function coherently, further cementing the speed barrier. Photons, or light particles, can travel at the speed of light because they are massless. Everything else in the universe, from atoms to spacecraft, possesses mass and is therefore bound to speeds below circa. This is precisely why photons can traverse the vast cosmos to reach our eyes, allowing us to view galaxies millions of light years away. Yet, even for photons, the journey requires time, limited to the number of years dictated by the speed of light. In certain scenarios, particles appear to exceed the speed of light, but this is an effective phenomenon within a medium. In water or glass, light slows down. If a charged particle travels through that medium faster than the light in that medium, it produces Cherenkov radiation. This does not violate relativity because the speed limit of light in a vacuum remains insurmountable. The Higgs field is also fundamentally linked to the inability to reach light speed. It imparts mass to particles. Without it, only massless particles, like photons, could travel at circa. For massive particles, the Higgs field acts as a kind of cosmic molasses, preventing them from being accelerated to light speed, a fundamental mechanism of the universe's operation. What, then, about cosmic expansion? Following the Big Bang, the universe underwent an epoch of inflation where space itself expanded faster than the speed of light. This does not violate the speed limit because it is the stretching of space that is superluminal, not the movement of objects through space. Similarly, gravitational waves, Ripples in spacetime caused by massive cosmic events propagate at the speed of light, further underscoring the physicality of the speed limit. On the propulsion front, the light speed barrier is a major obstacle. Even accelerating a spacecraft to 1/10 the speed of light could require energy approaching humanity's total annual energy consumption. This is why scientists are exploring non-traditional propulsion methods like solar sails and antimatter engines, seeking to circumvent the limitations of carrying fuel. Cosmic rays provide a natural sample of particles moving near the speed of light. Originating from high-energy events like supernovae, they reach astonishing velocities, yet always approach but never touch the speed of light, serving as a visceral demonstration of nature's limit on energy and velocity. Observing cosmic rays helps us understand the challenges of high-speed travel and particle behavior under extreme conditions. Information transfer is also bound by the speed of light. Even if a signal were sent at sea, it would take over 4 years to reach Alpha Centauri and another 4 years for a response to return, making a simple question and answer exchange nearly a decade-long process. Thus, interstellar mission spacecraft require a high degree of autonomy, as real-time communication is simply not feasible. Quantum entanglement is often mistakenly cited as a loophole for faster-than-light communication. However, despite entangled particles showing instantaneous correlation, no usable information can be transmitted, making it impossible to bypass the light speed restriction. Ultimately, the speed of light shapes how we view the cosmos. The distant galaxies we see are the way they looked millions or billions of years ago. This look back in time reveals the history of the universe and reminds us of the vast expanse of spacetime that separates us from the stars. Certain theoretical concepts, such as the Alcubierre warp drive, hypothesize equivalent faster-than-light travel by bending spacetime, not by making the spacecraft move rapidly through space, but by compressing space in front of it and expanding space behind it. This idea is mathematically compelling, but the energy requirements and the need for exotic matter far exceed our current reality. Material science and engineering also impose strict limits on near-light speed flight. Even microscopic dust particles, when encountered at extremely high relative velocities, become high-energy projectiles. A single such collision could critically damage the spacecraft, necessitating robust shielding and impact-resistant designs. Thus, the light speed barrier is not merely a physical limit but a methodological constraint on how we understand the universe and our place within it. It compels us to innovate and think outside the box, constantly reminding us of the immense gulf in scale and complexity. As we delve deeper into the concept of interstellar travel, time dilation emerges as a core, game-changing concept. Unlike the uniform passage of time on the ground, time is warped under high velocity and strong gravity. For a traveler journeying to a neighboring star at relativistic speeds, this effect will dominate the entire trip. Time dilation is more than just slowing down, it fundamentally alters perception. A near-light speed traveler will observe the pace of celestial events differently from those on Earth. The slow, steady evolution of galaxies on Earth may appear accelerated to them. This is not just a visual difference, it impacts how onboard scientists interpret the universe, pushing the boundaries of observational science. One particularly significant effect is the change in the observation of the cosmic microwave background (CMB). At near light speeds, the normally invisible CMB would be blue shifted into higher energy wavelengths, potentially entering the dangerous X-ray range. Coupled with the intense bombardment of cosmic rays, the spacecraft must employ enhanced radiation shielding. For the human body, time dilation means physiological processes slow down relative to Earth, a seeming benefit, yet one that carries unknown risks. Whether DNA stability might undergo unexpected changes under this time scale shift remains a critical area for future research. The human brain will also face challenges. Memory encoding and perception may need to adapt to long-term relativistic environments. When the traveler's timeline is compressed and the Earth's is stretched, how does cognition adjust? Perhaps creating simulated temporal environments on board could provide psychological anchors, though this may not fully eliminate the profound chronological shock. The relativistic Doppler effect compounds the challenge. The color and brightness of starlight shift dramatically from the traveler's perspective. Blue-shifted stars appear brighter and more energetic, while red-shifted targets become dim and fade away. Instruments must be recalibrated, and data processing needs real-time correction. Beyond light, the radio signals between the spacecraft and Earth will also be stretched or compressed, forcing the communication system to constantly adapt to shifting frequencies to ensure clear decoding, which is paramount for maintaining contact across vast distances. Navigating under time dilation requires a complete recalculation of basic assumptions. Pulsars, which act as cosmic lighthouses, will appear to have a skewed rhythm onboard due to relativistic effects. Orbital corrections must simultaneously incorporate the spacecraft's velocity and the observed change in the pulsar signal. The high speed compresses celestial events, from the full life cycle of stars to galactic mergers. Within the traveler's observable time frame, they might witness an accelerated version of cosmic processes. While awe-inspiring, this makes navigation and predictive models far more complex. Time dilation also offers seeming advantages. In the traveler's reference frame under relativity, high-velocity particles like micrometeoroids might present a different threat window, but this is no reason for complacency. The ship's structure must still be prepared for extreme impacts. Radiation exposure remains a persistent risk. As the traveler's time is compressed, the intensity and frequency distribution of cosmic rays also change. Magnetic shielding and new materials like graphene will become essential for survival. Even within the same spacecraft, time dilation might be non-uniform. Small differences in location, velocity, and gravitational potential could cause different parts to run out of sync. For instance, the propulsion section and the crew cabin might accumulate millisecond time differences over a long journey, necessitating extreme synchronization and fault tolerance. Another often overlooked consequence is the cascading effect on astronomical mapping. Stars are not stationary. The galactic drift over centuries means the destination star system will have altered its appearance upon arrival. The stellar map must update with the journey, making AI-driven, real-time celestial cartography critical. For the crew, time dilation means a profound social and emotional disconnect. Decades or centuries may have passed on Earth, family and friends are gone, and society has drastically changed. This is not a logistical problem but a psychological and ethical test for human resettlement. Scientific progress on Earth may also outpace the crew's original knowledge base, necessitating a system for compressed knowledge updates to sync Earth's findings with the crew in a limited time frame. Near-light-speed travelers may personally experience phenomena that Earth-based astronomy can only simulate, such as galactic mergers, supernova explosions, or the birth of new stars, all potentially unfolding within the journey's time window. However, the relativistic distortion requires powerful computational models to interpret these events and place the ship's observations back into the larger cosmic context. A deeper layer is the ethical question: given the psychological toll of multi-decade isolation and the potential difficulty of return, should we prioritize uncrewed probes? The potential for discovery must be weighed against the human cost. Returning travelers will be strangers, and societal reintegration must be planned in advance. To bridge interstellar distances, conventional chemical rockets are woefully insufficient. They lack the speed, the specific impulse, and the longevity required. Scientists and engineers are therefore exploring a range of boundary-pushing propulsion methods, each with trade-offs, collectively pointing toward the interstellar age. One of the simplest and most promising is the light sail, which uses the momentum of photons from the sun or a laser to push the spacecraft. Photons, though massless, carry momentum, which exerts a tiny but continuous force when reflecting off a highly reflective, thin sail. This requires no onboard fuel, and the ship can accelerate for years by angling its sail. Experiments have already been conducted on small-scale planetary missions. If scaled up and directed by massive Earth or space-based laser arrays, much higher speeds could be achieved. Breakthrough Starshot, for example, aims to use high-power lasers to propel microprobes to Proxima Centauri within decades. The challenge lies in laser power, array scale, and precision pointing across light years. Magnetic sails (magsails) use a gigantic magnetic field to deflect charged particles, providing continuous thrust while also offering a degree of radiation protection, making them suitable for the outer solar system. For higher thrust and continuous acceleration, attention turns to fusion propulsion, which utilizes controlled nuclear fusion of light elements to release immense energy, ejecting high-velocity plasma for thrust. The difficulty lies in achieving ignition, confinement, and efficiency in a controllable manner. Current experiments, like ITER, focus on energy production. Converting this to space propulsion requires miniaturization, thermal management, and pulsed control. Among fusion fuels, helium-3 is attractive. It could potentially be harvested from the Moon or giant planets and produces less radiation. Antimatter propulsion represents the ultimate, far-future vision. The energy density from matter-antimatter annihilation is nearly perfect. A small amount of antimatter could propel a probe to a significant fraction of light speed. The current obstacles are enormous. Antimatter production is extremely low, cost is prohibitive, and storage is incredibly difficult, requiring magnetic or electric traps to isolate it from ordinary matter and prevent annihilation. Muon-catalyzed fusion is a more experimental pathway that uses muons to lower the fusion barrier, allowing fusion to occur at lower temperatures and pressures, potentially increasing propulsion feasibility, but it is in the very early research stages. Beamed energy propulsion offers an alternative approach. Earth or space-based laser or microwave arrays remotely transmit energy to the spacecraft. The ship carries little fuel, resulting in a lighter mass and higher efficiency. The cost is the massive ground infrastructure and the need for extremely high pointing accuracy. Nuclear thermal rockets (NTR) use a reactor to heat propellant gas, which is then ejected at high velocity. They offer a specific impulse higher than chemical rockets and serve as a transitional step toward more advanced propulsion. Electric propulsion ion thrusters, though low in thrust, have extremely high specific impulse, ideal for continuous, gentle acceleration over long periods, making them one of the existing cornerstones for long-duration deep space missions. The Bussard ramjet is perhaps the boldest concept, using a gigantic magnetic field to scoop up interstellar hydrogen from the interstellar medium and use it as fusion fuel for continuous propulsion. The advantage is that no fuel needs to be carried for the entire journey. The difficulty is the extremely low density of interstellar hydrogen and the enormous scale of the required magnetic field. Photon thrusters use lasers or other light sources to directly provide momentum. Though the force is minute, they are extremely efficient and suitable for high-speed delivery of micro or nanoscale probes. Once speeds approach relativistic velocities, propulsion enters a new physics regime. Energy requirements increase exponentially, and particulate collisions become lethal. Propulsion systems must work in deep synergy with protection, navigation, and sensing. A hybrid propulsion system is a pragmatic strategy, for example, initiating the journey with a light sail before transitioning to fusion cruising, or combining a magnetic sail for thrust and radiation protection. Such combined approaches leverage the strengths of each system during different phases. There are also more cutting-edge concepts, exploring new avenues for electromagnetic propulsion by harnessing energy from the quantum vacuum, utilizing plasma propulsion to control plasma flows via magnetohydrodynamics, and developing in situ resource utilization (ISRU) systems that collect and regenerate propellant during flight to drastically reduce initial launch mass. For crewed long-duration flights, active and sustained acceleration can simulate gravity, mitigating the damage caused by microgravity. Miniature spacecraft can utilize laser ablation propulsion, where lasers vaporize the ship's surface material to generate a recoil force, ideal for high-precision maneuvers in micro-missions. In sum, from photons to quantum physics, and from sails to fusion, innovations in propulsion are the key to breaking out of the solar system and embracing the interstellar frontier. Navigating the interstellar ocean is an extreme challenge in both science and engineering. Unlike terrestrial or planetary navigation, interstellar travel demands systems that operate autonomously for decades, even centuries. Pulsars, the rapidly spinning neutron star remnants of massive star explosions, emit highly regular radio pulses, acting as cosmic lighthouses that allow the spacecraft to self-locate, akin to ancient mariners navigating by the stars, serving as a galactic GPS. Their accuracy can reach millisecond precision. However, pulsars are subject to occasional glitches and period drift, requiring the spacecraft to continuously recalibrate en route. More challenging is celestial proper motion. Stars are not stationary, and over decades or centuries of long-haul flight, the target star's position will shift significantly. The mission must rely on high-precision three-dimensional star catalogs to predict future positions and continuously update these maps during the journey. The density of the interstellar medium (ISM) is not uniform. Dense regions exert a slight drag on the spacecraft and can erode sensitive instruments. The ship must be equipped with forward-facing sensors to map local structures in real time and navigate around them. Micrometeoroids pose another threat. Even a grain of sand is potent enough to pierce a hull at near light speed relative velocities. Beyond robust materials and Whipple shields, the navigation system must identify high-density particulate zones and actively divert to avoid impact. Artificial intelligence (AI) is crucial, processing vast amounts of data in real time, identifying threats, and correcting the trajectory at speeds unattainable by humans. Inertial navigation allows the spacecraft to maintain its course during communication blackouts, but accumulated errors over years are inevitable, requiring repeated correction via pulsars and star catalogs. Near light speed travel introduces relativistic effects. The spacecraft's clock is desynchronized from Earth's, and the Doppler effect alters communication frequencies. Navigation and communication systems must incorporate relativistic correction algorithms. Quasars, due to their immense distance, maintain a highly stable relative position and can serve as deep space coordinates, complementing the pulsar system. Energy efficiency is also non-negotiable. Gravity assists can reduce energy consumption, but on an interstellar scale, they require extreme precision and long-term planning to avoid overshooting or veering off course. Intriguing concepts also include cosmic microwave background (CMB) navigation, utilizing its slight anisotropy as a large-scale positional reference. While still theoretical, it is worth exploring. The golden rule of interstellar navigation is redundancy. No single system can sustain a multi-decade mission. Pulsar guidance, stellar maps, and quasars should be used in parallel, with full backup and graceful degradation protocols for all propulsion, communication, and navigation hardware. In the far future, we may leave behind navigation beacons in the interstellar medium for later missions, gradually weaving a cosmic highway. The greatest difficulty in interstellar communication is the light speed delay. Even at the speed of light, a one-way trip from Earth to Proxima Centauri takes over 4 years, meaning a simple exchange takes nearly a decade. In contrast, Mars communication delay is only 4 to 24 minutes. This immense time lag forces the spacecraft to operate with a high degree of autonomy, rendering ground real-time remote control impossible. AI will act as the ship's brain, making predictive, preemptive decisions based on forecasting models. When real-time data return is impossible, the AI must autonomously manage anomalies while prioritizing data transmission by importance, sending crucial discoveries first, with other data following later in highly redundant transmissions. Laser communication provides a focused, low-divergence link over long distances, offering better signal-to-noise ratio than traditional radio waves. Project Starshot also proposes using the propulsion laser array to transmit data back to Earth. Interstellar dust and radiation will perturb signals. Dual wavelength, multi-frequency encoding and high redundancy can enhance reliability. The interstellar relay network is another approach, deploying autonomous beacon probes along the path to form a relay chain, an interstellar scale expansion of the concept used for Mars communication. Quantum communication holds fascinating promise, but current constraints are real. Entanglement cannot transmit usable information, and the challenge of maintaining decoherence-free entanglement across interstellar distances remains immense, making faster-than-light communication unfeasible in the short term. Data compression and mission design are equally important. Given the slow turnaround, experiments must be prioritized to generate clear, unequivocal signals, maximizing information with minimal interaction. For example, first sending back atmospheric survey spectra and images to confirm potential biosignatures, allowing ground analysis to send back second stage, high-fidelity sampling commands. Energy is the lifeline of communication. Solar power degrades significantly in the outer system, necessitating long-life nuclear power sources or new energy storage solutions. In a high-energy cosmic environment, robust error-correcting codes and interstellar channel modeling are indispensable. Predictive communication should also be developed. The spacecraft, based on mission rhythms and likely ground questions, pre-packages answers to upload, saving valuable round-trip time. More profoundly, the mindset and goals must be reshaped. Interstellar missions should focus on low-interaction, high-value scientific pursuits like long-term evolutionary observations rather than frequent, question-and-answer style control. The value of interstellar missions extends far beyond mere arrival. They address fundamental questions about life, physics, and geology. In the search for life, biosignatures are not limited to oxygen. Gases like dimethyl sulfide and phosphine, produced under specific conditions by microbes, are equally critical. High-resolution spectroscopy can dismantle atmospheric composition from light years away, building environmental profiles. Direct imaging, aided by coronagraphs and star shade technology, can suppress stellar glare to resolve the planetary disk, providing coarse resolution clues on oceans, continents, ice caps, or deserts, aiding habitability assessment before landing. On the climate front, long-term monitoring of seasonal, temperature, and circulation changes reveals climate stability, a key factor for habitability. Different axial tilts and orbital parameters will shape the planetary seasons. Stellar physics is also paramount. The magnetic field and high-energy radiation of a neighboring system directly impact planetary atmospheric retention and surface environment. Geomapping involves high-resolution topography, signs of river channels, impact craters, and volcanic activity, all clues to geological activity. The discovery of subsurface liquid water is strong evidence for past or present habitability. The gravitational dance in binary star systems shapes the stable and unstable orbital zones for planets, affecting their formation and long-term stability. The planetary magnetic field is a shield for life. Measuring magnetosphere strength assesses the atmosphere and life's resilience to the stellar wind. Interstellar visitors carrying unusual material compositions offer a window into cross-stellar seeding. Sampling them helps understand how the building blocks of life flow between star systems. On a larger scale, collecting particles and organic molecules from the interstellar medium reveals the starting points of prebiotic chemistry in harsh environments. Tidal heating shapes subsurface environments. Planets close to their stars might be geologically active due to tidal forces, potentially maintaining internal liquid oceans even if their surface is frozen. Protoplanetary disks in young stellar systems show the ongoing process of stellar ignition and planetary accretion, completing our retrospective view of the solar system's formation. Photochemical reactions change atmospheric chemistry under stellar irradiation, shaping habitability. Long-term monitoring can map their evolutionary paths. Interstellar probes can also place new constraints on fundamental puzzles like dark energy and dark matter. Measurements in different gravitational fields and space environments might reveal new physics. Planetary rotation and axial tilt determine day-night cycles, seasons, and weather patterns, fundamental pieces in the puzzle of fully understanding a terrestrial ecosystem. Interstellar journeys can incidentally capture close-up details of high-energy events like gamma-ray bursts and supernovae, crucial for understanding heavy element synthesis and galactic chemical evolution. The secrets beneath the surface can be revealed by penetrating radar and seismic detection, seeking subsurface oceans and layered structures. Testing whether physical constants like the speed of light and the gravitational constant are indeed constant across different cosmic environments is a fundamental scientific test. Building an interstellar probe is not merely assembling a spacecraft but creating a scientific platform capable of operating stably for decades in the unforgiving cosmos. The core lies in miniaturization, efficiency, and adaptability. Miniaturization and nanotechnology are the bedrock, reducing mass without sacrificing function, which lessens the propulsion burden. Microspectrometers and radiation detectors can form a comprehensive, lightweight scientific payload. For power, solar energy wanes significantly farther from the star. Long-life nuclear power sources, future small-scale fusion generators, and high-density energy storage will be critical. If fusion is realized, it offers long-duration cruising with minimal refueling. Radiation and high-energy particles are the bane of electronic systems. Radiation-hardened materials, from graphene to specialized coatings, extend mission life. Thermal control is often overlooked. Heat is difficult to dissipate in a vacuum, requiring efficient radiators and insulation to prevent overheating of electronic and propulsion systems. High-velocity impacts from micrometeoroids and dust are inevitable, demanding impact-resistant and self-healing materials to reduce the probability of single-point failure. Navigation must be self-sufficient. Pulsar navigation combined with high-precision star trackers allows the probe to orient itself during solitary flight. Communication requires high autonomy and high bandwidth, long-range laser links, strong error correction, and large-capacity storage, ensuring data integrity regardless of whether data is stored and forwarded or prioritized for immediate transmission. AI enables autonomous driving, real-time analysis of scientific observations, active hazard avoidance, and dynamic selection of research targets, minimizing waiting for ground intervention. The scientific payload must be tailored, from high-resolution cameras to atmospheric spectrometers, all serving the goal of understanding the target system. Deployable mini-probes can conduct close-range reconnaissance of planetary surfaces or asteroid belts. On the materials science front, radiation-hardened alloys, reinforced composites, and advanced ceramics work together to be both light and tough. The interstellar medium is non-uniform, requiring the probe to continuously monitor and self-adjust its trajectory and operational parameters. Modularity is one answer to long life, allowing for staged upgrades in subsequent missions, ensuring the probe retains cutting-edge capability decades later. Cost and international collaboration are also paramount, balancing innovation with affordability, sharing funding and technology through multinational partnerships. The propulsion system and overall design must be synergized. Sails need to be light, fusion needs powerful heat dissipation, with each system requiring dedicated support. The ultimate goal is not just arrival, but bringing back data that changes our fundamental understanding. Interstellar travel forces us to reckon with epical timescales. Target stars and interstellar clouds will change position and activity status under the banner of proper motion, precise gravitational motion models, and continuous recalculation by the onboard AI must span the entire journey. The target star itself evolves. Flare activity, luminosity shifts, and magnetic fields change the planetary environment. What seems habitable today may be inhospitable upon arrival, requiring onboard instruments to continuously evaluate habitability en route. If the mission is crewed and spans centuries, a multi-generational ship is inevitable, necessitating genetic diversity management to maintain group health and closed-loop life support. Bioregenerative life support systems for microbes, plants, and humans maintain long-term stability through water, air, and nutrient cycling. Hydroponics, aquaponics, and synthetic biology will provide compact, efficient ecological modules. The continuation of knowledge and culture must also be engineered. Radiation-hardened, ultra-high-density quantum storage and other technologies carry humanity's science, art, and history for onboard education and cultural continuity. Self-repairing materials, radiation shielding, and rapid damage localization repair systems defend against long-term environmental degradation. Psychology and culture also require design. Virtual Earth environments, companion narratives, and rituals help successive generations maintain a stable identity and sense of purpose. Suspended animation or stasis technology is one alternative for multi-generational missions. Research into extremophile cryoprotectants may inspire non-destructive tissue preservation. AI may serve as the governance backbone, with self-learning and evolutionary capabilities to maintain institutional continuity and fairness across generations. The long-term threat of cosmic radiation to health and electronics requires a dual solution of magnetic shielding combined with anti-flux materials. The education system must be adaptable, with AI tutors and adaptive curricula ensuring the transmission of technology and mission understanding across generations. Onboard small-scale terraforming experiments in controlled environments can evolve a complete process for stabilizing atmosphere, temperature, and biosphere. Ethical preparation for meeting intelligent life is essential. Contact protocols, non-interference, and reciprocity frameworks must be clarified before launch. In-transit resource acquisition will boost range and reduce launch mass. Stellar slingshots remain useful on an interstellar scale, utilizing flybys around stars to alter velocity and direction. Long-term low gravity and radiation exposure may induce epigenetic changes, requiring monitoring and intervention. Intergenerational ethics hinges on consent and autonomy. How will the decisions of the first generation constrain the lives of their descendants, and how is mission versus freedom balanced? Earth-like day, night, and gravity cycles are critical for psychological well-being. Ultimately, having the capacity for return or repurposing provides strategic flexibility for multi-generational missions. The risks on the interstellar path stem from the very nature of the cosmos. High-energy cosmic rays can penetrate shielding, damaging DNA and electronic systems. Thicker shielding is safer but adds prohibitive mass, and metallic shielding often generates secondary radiation, necessitating composite materials like polyethylene, which produce fewer secondary particles. Micrometeoroids and dust are lethal at high speeds, requiring impact-resistant structures and active detection avoidance systems. Uncrewed missions rely on redundancy. Crewed missions need robust real-time monitoring plus in-orbit repair. Capabilities: stellar X-rays, UV, and stellar windy road materials and instruments when passing active stars. Specialized material coatings and stellar weather forecasting must be integrated into mission design. The interstellar medium is not truly empty. At relativistic speeds, hydrogen atoms can cause thermal deposition on the hull, threatening sensitive components. Dense dust patches cause signal attenuation and occultation, requiring the ship to have a deep space radar for the medium. Plasma environments can interfere with electronics and communication, demanding electromagnetic shielding and robust architecture. Gravitational anomalies can alter the course, relying on precise gravitational models, and pulsar-quasar triangulation is necessary to maintain trajectory. Propulsion systems are sensitive to their environment. Sudden changes in plasma flow or density can affect ion and plasma thrusters, requiring adaptive thrust control. At relativistic speeds, the reaction time for discovering and avoiding hazards shrinks dramatically. Preemptive prediction and immediate course correction are vital. Temperature extremes test thermal control, and long-term electrical charge accumulation threatens electronics, requiring excellent grounding and static management. Gamma-ray bursts are rare but catastrophic if encountered head-on, requiring extreme event preparedness. These risks are not insurmountable, but they underscore that interstellar missions must approach uncertainty with a combination of hard technology, meticulous planning, and profound human-AI collaboration for safety. That concludes our discussion for today. I wish you all sweet dreams and a wonderful day. We will see you next time.